Assalamu alaikum everyone. Today we are going to talk about the synchronous motor. We will discuss its basic operating principle and then we'll discuss its applications as well. So let's get started. So synchronous motor from the construction point of view is no different from the synchronous generator. It theoretically speaking, both synchronous generator and synchronous motor are in fact the same devices, with the only difference being the reverse of the power flow. So the construction wise, it consists of stator, the three-phase stator, which basically generates the rotating magnetic field when there is a current flowing through the armature windings. So just to point out, the armature is on the stator here. So this is armature winding, and it has the rotor, which is basically a permanent magnet. So just a quick recall that we learned previously in AC generators that three-phase winding generates a rotating magnetic field inside the stator. So for example, if we have a three-phase winding here, so it means this will generate a rotating magnetic field vector. So this is the magnetic field which is produced by the stator. So we call this vector as a BS. We also said that this vector can be imagined by having an imaginary north and south pole, which is running along on the outer rim of the stator. Okay. So if this vector is rotating counterclockwise, it means these poles, the imaginary poles, are moving counterclockwise. So you have a south pole and you have the north pole, which is rotating. Okay. And that's why you have the direction of the magnetic field pointing towards the south pole. So if we introduce a rotor into our circuit, so as we know, rotor in the case of synchronous machines is also it can be simply a permanent magnet which has its own north and south pole. So for example, this is the rotor, and in this configuration we can say this is the north pole of the rotor and this is the south pole of the rotor. And it doesn't matter whether the rotor is a permanent magnet or whether it's electromagnet supplied by the DC power. So as you can see, the north pole and south pole here are aligned in this case. So it means as these imaginary poles rotate along the stator, so this rotor magnet is going to be always attracted towards these imaginary south pole, and this is going to be always attracted towards the imaginary north pole. It means if we run this machine, then it's going to continuously follow the rotating magnetic field vector which is supplied by the stator. So let's run the simulation again. So we have a rotating magnetic field which is produced by the stator, and we have a permanent magnet which produces the rotor magnetic field as represented by BR here. So it means if we run this motor and if we see this in real time, we'll see this coupling between the stator magnetic field and the rotor magnetic field. So we call this as a magnetic locking. With this coupling is called the magnetic locking. Okay. So the stator magnetic field is locked with the rotor magnetic field, and the rotor basically tries to follow or catch up with the stator magnetic field. So that's basically the working principle of the synchronous motor. So the synchronous machine is essentially the same machine as synchronous motor is the same as a synchronous generator, only that it converts that electrical power to the mechanical power, whereas the generator converts the mechanical power to the electrical power. So in that, the rotor we discussed K, it tries to catch up the stator magnetic field, and larger the angle between the two magnetic fields, there will be a more torque produced on the rotor, which will ensure that the both magnetic fields stay aligned, which will ensure that the both magnetic fields stay in locked condition. So a synchronous machine is basically, as we said, it's the same as a synchronous generator. It means all the laws and the principles and the equations which we derive for the speed, power and torque, that will be valid for the synchronous motor as well. So one thing that I want to specify here, that will since we already know the working principle and all the fundamentals, we already covered all the fundamentals of the three-phase synchronous machine in the synchronous generator, so we'll not repeat the same ideas here, but rather our goal here in the synchronous motor will be to cover the synchronous motor with the lens of the application, that how this motor is used. This is indeed an interesting piece of a machine, which is basically not only used for the purpose of the motor, but it is also used for the numerous applications like the power factor correction. Okay? So we'll discuss those as well. So if you see on your right side, as we said, the rotor of the synchronous motor can be a permanent magnet, and the stator would be a three-phase winding, which are connected to a three-phase supply. Also, the rotor could also be an electromagnet, where this there will be a coil on the rotor which will be supplied the DC power. So now the same ideas will stay true that we learn in the case of a DC generator, that you can supply this DC power with the help of slip rings, or you can also supply the DC power with the help of a brushless exciter. So let's see one more figure here that of the synchronous motor. You can see in this figure that the slip ring and brush mechanism, which is basically these strips are your slip rings, and the carbon brushes which are connected. So these are basically supplying the DC power to the field winding which is on the rotor. Now I just want to quickly discuss some of the key characteristics of the synchronous motor, which makes this motor a very interesting piece of a device. So the synchronous motor runs at what we call the synchronous speed, and the synchronous speed is given by this formula which we derived in the synchronous generator. It's the same formula, we only saying that synchronous speed will be depending upon the electrical frequency and the number of poles in the machine. So it means, so what does this equation mean is that the only way to change the speed of the synchronous motor is to either change the number of poles, either change the number of poles or you change the electrical frequency of your power, of your electric power, change the electrical frequency. Right, so it means if your number of poles are fixed, which usually are, and you are supplying with a constant three-phase power supply, it means constant frequency three-phase power supply, which usually we have. So it means the speed of the synchronous motor will not change with respect to the load. Okay, so that's very interesting characteristic, and that makes it very useful. And this is where the word synchronous comes from, that it's the speed, the mechanical speed of the motor is synchronized with the electrical frequency of the power supply. So your motor can only run at the synchronous speed, it cannot run at any other speed. So that's a very interesting characteristic. So we'll discuss that again when we summarize the different behaviors. So, and the second thing about synchronous motor is that the synchronous motor is not inherently self-starting. So it means that if you just power on the if you just connect the three-phase power supply to the synchronous motor, the motor will not start by itself. Okay, it needs an additional mechanism to start it. So in order to first understand why this is not inherently self-starting, so let's see the animation again. So we have the same animation. इसके अंदर we earlier we when we run the animation, we assumed that the rotor was the rotor didn't had the inertia, or you can say that the rotor was already rotating at the synchronous speed. Okay, so then at that point your rotor will be following the stator's magnetic field. But if your rotor is at the stationary point and the rotor usually has load connected in it as a significant inertia, it means that when your stator's magnetic field vary, so your rotor will not be able to catch up because of the inertia. It will slightly turn towards along in the direction of the rotating magnetic field, but after a certain time there will be, so for example in this particular snapshot you can see now the rotor magnetic field is completely opposite the stator's magnetic field. So it means this picture can be better understood if we place our imaginary north and south pole. So if we have a north pole and south pole of the rotor, and the stator's north pole and south pole, so this will be the stator's south pole and this will be the stator's north pole. Okay, so this is how we imagine the rotor's magnetic field. So it means now you can see that this south will repel this south. Okay, so it means that now instead of causing the rotor to rotate in the counterclockwise, when the rotating magnetic field moves further in this direction, it will actually repel this rotor in this direction. It means that if our vector goes again back, so it will try to repel it and bring it to the original position. So what will happen is that the rotor will continuously vibrate along the mean position. It will not be able to catch up the speed of along the it will not be able to catch up the speed with the speed of the stator's rotating magnetic field. It means that in order to start a synchronous motor, so first thing is the synchronous motor is not self-starting. So if you want to start a synchronous motor, so the one way is to bring the rotor's speed up to the synchronous speed by some mechanism, and then we leave it to the then we just then we just remove the mechanism and let the rotor's magnetic field catch up with the stator's magnetic field. So that's the one way to start the synchronous motor. So we'll discuss more about the starting mechanisms of the synchronous motors. Okay, how can we actually, so this was the the basic principle which suggests from the intuitions that how we should start the synchronous motor. So it means that we have a very important characteristic of a synchronous motor, that the synchronous motor runs at the synchronous speed or not at all. It means the speed at which the synchronous motor can run is only the synchronous speed. Okay, so the motor cannot run beyond the synchronous speed or below the synchronous speed even though when the load changes. So this is very important characteristic which is seen in synchronous motor. Okay, so let's now move ahead towards the equivalent circuit diagram of the synchronous motor. So equivalent circuit diagram is not much different from the circuit diagram of the synchronous generator. So the only thing that is different now is the reverse of the power flow or the reverse of the direction of the current, the armature current. So if you reverse the direction of the armature current, then your this sign, which was in the case of generator, this was plus, now it becomes the minus. So this is for the case of the motors, but for the generators those were minuses here. So it means the phase sub power will be equal to the the back EMF plus the IR drop and the IXS drop. Okay, so that will give you the equivalent circuit, and the field circuit stays the same for the synchronous motor and synchronous generator. You provide the DC power in both cases, and you have the field resistance and the variable resistance there. Okay, so we now are up to the mark with the synchronous motor. That the synchronous motor, we got the model of the synchronous motor, we got the speed characteristic of the synchronous motor. Okay, so let's now see the torque characteristics of the synchronous motor. So if we see the torque speed characteristics, as we said, the synchronous motor runs only at the synchronous speed. It means the characteristic curve should be a perfectly vertical line, right? So you can have any torque that you want along this line, as long as you are operating under the rated torque. And so it means but your speed cannot vary. The speed of the synchronous motor cannot vary, so that means that this line will be perfectly vertical line. So the speed regulation in the case of a synchronous motor is equal to 0. Okay, so then the no load and full load speed will be always equal, because the synchronous motor either runs at the synchronous speed or not at all. Okay, so that's the principle. Okay, so and we also know these equations that we derived in our synchronous generator. As we said, that these equations will also be valid in the case of the synchronous motor, and we know that the torque induced in the case of a synchronous machine is that the 3V phase EA sine sigma divided by omega m divided by xs, where sigma is the torque angle, where the sigma is torque angle. So as you vary the torque angle, you will have a more output torque. So the maximum torque that occurs will be at when sigma is equal to 90 degree, and that torque is called the pull-out torque. So the pull-out torque is basically the torque at which rotor can no longer remain locked to the stator, and so basically the motor stops at this point. Okay, so in this diagram we have a assumption imposed here that the synchronous motor is connected to the infinite bus. So what is an infinite bus? Is the one which, so infinite bus is basically the power source. So it's the power source whose terminal voltage and the frequency does not change with the load connected. Okay, so it means so the primarily what do we want when we are studying the characteristics of the torque speed characteristics of the synchronous motor, we do not want the terminal voltage or frequency to change from the power supply, from the power source. So you have the synchronous motor which is being supplied power from some power source. So for example, if it's a single power source like a synchronous generator, जैसे हमने discuss किया था, and we know from the synchronous generator's discussion that as the load increases, it reduces its output. The terminal voltage reduces for the synchronous generator. So it means if this is connected to the synchronous motor, if the motor draws more power, then it will reduce the terminal voltage. That we do not want. We are assuming our generator is so we have an infinite bus. It means our voltage is not dropping as we are increasing the increasing the load on the motor. Okay, it means when we are drawing more currents, the voltage, terminal voltage does not drop. So what does it say? And also it also imposes that the frequency does not change. For in the case of standalone synchronous generator, we discussed case the frequency is concerned with the governor, but in case of the parallel generators, when you draw the more current, so the frequency of the generators also change. Okay, so that we also impose that the frequency supplied by the power source, whatever the power source is, that to the synchronous motor, that stays same, and the voltage supplied, that stays same as well. So in those cases you will have these characteristics. So we discussed that the pull-out torque is the torque which basically at that point the motor cannot follow the rotor's magnetic field cannot follow the stator's magnetic field. At that point we our magnetic fields will be unlocked. It means the rotor will not be able to follow the stator. So that condition is called the slipping poles. Your rotor is basically continuously slipping. The rotor's magnetic field is continuously slipping behind the stator's magnetic field. It means that phenomena will again be observed, which I showed you in the animation, that as you increase the load beyond the pull-out torque, the rotor will again vibrate, because the rotor's magnetic field will not be able to catch up with the stator's magnetic field. So that phenomena is called the slipping poles. Okay, so we said that the pull-out torque, the torque induced, which is the pull-out torque, that is basically happens when sigma is equal to 90 degree. It means this is equal to 3v phase EA divided by omega m xs. So one thing that you can say from all this discussion is that this pull-out torque is basically depends upon some fixed quantities, which is the xs, which is fixed because it depends upon the construction, and omega m is basically fixed by the synchronous speed, which is the speed of the rotation, and v phi, if you are connecting your synchronous motor with the infinite bus, it means that v phi is also fixed. It means the only way you can vary the maximum torque or the pull-out torque, you can increase the pull-out, you can basically increase and decrease the pull-out torque by increasing or decreasing the EA. And how can you increase or decrease the EA is by increasing or decreasing the field current. Okay, so you remember that EA is basically your K phi times omega. You cannot vary omega here because the motor will always operate at the synchronous speed. So the way you can increase or decrease the pull-out torque is by increasing or decreasing the flux, which you can vary by increasing or decreasing the field current that is being supplied to the rotor's winding. Okay, so next we'll that's our goal for the next point. Okay, how does the field current affects the characteristics of the synchronous motor? Okay, so that's the one behavior that we saw, that as you increase the field current, you'll have a more pull-out torque. But we want to see more into the details of it. Okay, we know this equation for the synchronous motor, that the phase voltage is equal to EA plus JXS times IA plus RA times IA. So it means that if we draw the phasor diagram, so suppose we are our motor is usually considered as an inductive load. It means we are assuming that IA is lagging behind the V phase. So this is the power factor angle, which is the theta. It means that V phase will be equal to EA plus JXS IA plus RA. So if we ignore the IA RA drop, as we did in the case of synchronous generator, then we can basically combine these two vectors, which is IA XS plus EA, which will give us the V phase voltage. Okay, so that is our the phasor diagram for the synchronous motor. So what we want to study right now is that how the field current is going to affect the synchronous motor. So in order to see the effects of the field current, we need to impose certain conditions here, that we are ensuring that we are not changing other parameters. So we only want to study the effect of the field current. Okay, so what are the assumptions here? So assumption number 1 is that the synchronous motor is connected to the infinite bus. So let me clear the ink here. So it means that when we said the synchronous motor is connected to the infinite bus, that we just discussed that this point implies that the frequency and the phase, the voltage that is being supplied, cannot vary. So just remember that the V phase is basically the supplied voltage in case of a synchronous motor. So you have a equivalent circuit like this one, per phase equivalent circuit. So this is your V phase and this is your E. You are supplying basically V phase. So it means when you are connecting the synchronous motor to the infinite bus, you cannot vary the magnitude of the V phase. That is fixed. It means in this phasor diagram you cannot vary this point, okay, or you cannot vary the the length of this vector. So that is basically fixed, that is decided. Okay, V phase is always going to be this vector, okay. And since this is a phasor, our reference vector, it means this is going to be always horizontal and fixed to this length. It means this is always going to be the same vector, okay. This is what this assumption means. Okay, so our second assumption says that the same load is connected to the motor shaft. So now this is very important assumption. When we say that the same load is connected to the motor shaft, it means basically that the same torque. So indirectly it means that the same torque is connected to the motor shaft, okay. Same and it also means, because the speed cannot vary, it means the same real power is being supplied by the motor. So you remember that the real power is equal to torque times omega, and we said that the same load is connected to the motor shaft. It means the torque, this parameter cannot vary. This is already fixed because it's a synchronous motor. It means the real power that is being supplied by the synchronous motor, that cannot vary. Okay, so what does it mean by keeping the real power constant in this phasor diagram? So luckily we have this equation that which says real power is equal to 3 times V phase EA sine sigma divided by XS. So the other quantities are fixed, so already fixed. It means this quantity, which is EA sine sigma, that cannot vary now, okay. So that is what the condition number 2 implies, okay, that EA sine sigma cannot change. And what is EA sine sigma is basically, so this is your angle sigma, and it means if this is the vertical component, it means this vertical component is your EA sine sigma. So what we are saying is that component cannot change, okay. So the x component can vary, so this component can vary, which is EA cosine sigma. So that component can vary. So but the length of this vector cannot change. It means EA can only slide along this line, okay. And this is only way you can ensure that your EA जो है its sine sigma component cannot vary, okay. So that's what does this condition impose means. And also this condition basically means one more thing. If you remember, we derived this expression, the way we derived this formula was that the EA sine sigma was basically equal to IA XS cos theta, Okay, so in the case of synchronous generator, we derived this expression from the triangles. It means that you can again see the same expression here as well, that this is IA XS. Okay, and it means if this is the angle theta, then this component cannot vary. Okay, so it means what we are saying is that xia cos theta term cannot change as well. Okay, so this is the implication of the condition number 2. So the first is that ea only can slide along this line. And second implication is that ia cos theta is equal to constant. It means if this angle is our theta and this vector is ia, it means that this is the x component, this is ia cos theta. Okay, so this component. So what we are saying from the condition number 2 is that we cannot change the x component of, so it means when you have the same power, the x component will stay same. And it also means that when you have the same power drawn, same load connected, so the ea sine sigma vector will not change. So it means the only, so the variation now we can observe is the variation along this line, for the ia. It means ia can only change along this line. Okay, so now let's summarize when we vary the field current, so what can happen now. So we said we know this expression that ea is equal to k phi omega. Okay, and because omega is constant, phi depends upon the field current. It means if we increase the field current, we will be increasing the ea. Okay, so that's the one point that is coming now. And the second point that is coming from the assumption number 2 is that now ea can increase, but it cannot increase throughout the space, but it will only increase along this line. It means the ea vector can be this vector, can be this vector, can be this vector. So your ea is increasing, the magnitude is increasing, but still the y component stays the same, the ea sine sigma component. And this also means that and also one more condition that we have is the ia cos theta cannot change, it should stay same. So it means in order to ensure both conditions, the theta needs to vary. Okay, so the theta of the ia needs to vary such that this component stays the same. Okay, so it means to ensure these two conditions, the only way that ia cos theta can stay constant while varying, while having the variation, is that the magnitude of this vector changes, the magnitude of the current changes, and the phase angle stays. Phase angle, the power factor angle, that also changes, such that the product remains constant. Okay, so now we are ready to see our the variations in the diagram. So let me clear the screen. So from here you can see that when your ia1 is this vector, then the ea vector is this one, and as you increase the ea by increasing the field current, field ea directly depends upon the field current. Ea is supposed to increase when you increase the field current. It means it cannot go here, but it will go here in order to increase the magnitude. So it means if you just increase the ea, it make it to the ea2. Okay, so it means so now you have a condition that you are supposed to add this vector at the 90 degree to the ia. Okay, so this vector, So it means that the IA would be actually IA2 would be this point. Okay, and in that condition, so that vector will be perfectly perpendicular to ensure that this is connecting back to this point, because we also had the condition number 1 that V phase cannot change. Okay, so similarly, if you increase the EA, if you go further, it means the more IF you increase, the IEA will increase, and because of the increase in EA, the magnitude of IA first drops, then further increases such a way that IA cos theta stays same. Okay, so that is effect of the field current. So now the question is, how does it useful? What does it mean? So that's very interesting point. So now you can see clearly from this figure as well that as you are increasing the field current, you are basically decreasing the power factor of your system. Okay, so remember, the power factor depends upon the phase angle between the V phase and IA, which is the theta. Okay, so it means if you are increasing the field current, you are decreasing this angle. Okay, so you are also decreasing the power factor, and you are also decreasing the IA, so till the point when the power factor becomes the unity. Okay, and then if you further increase the IF, then the power factor will become the leading power factor. And so first it was the lagging power factor, then it was the leading power factor. So still, what's the importance of this? So now you have a motor. So motors are usually the inductive load, right? So as you might have recalled from the other courses as well, that motors are usually the RL load. Okay, but we now have a kind of a motor, the synchronous motor, which can behave like an inductive load, which can also behave like a unity power load, which is the resistive load. And not only that, it can also behave like a leading power factor load, like a capacitive load, and that is very strange. So it means that we can not only correct the power factor when you are operating the synchronous motor, but you can also use the synchronous motor as a device to correct the power factor for your system. So if you recall from the example that we did in the chapter number 1, when we were discussing the basis of the three electric power, there we discussed how do we correct the power factor. So if you have all the inductive loads, then you want to correct the power factor, you connect a capacitive load that will correct the power factor. Okay, so now you can see here that if you have all the motors that are operating into the machine and you want to correct the power factor, so the one way is to install a capacitor, which will be say not much useful to the industry. It will only do the power factor correction, but you will not be doing anything useful out of it. But here, in the case of a synchronous motor, you are operating a motor. You have a device which is a synchronous motor, which is operating as a motor, but with the power factor of the capacitive load. It means if you have other motors which are those are induction motor, which are working as a lagging power factor. So you can install one synchronous motor or two synchronous motor to do the power factor correction for the other induction motors, okay, or other kind of inductive loads. So that's a very interesting application. So let's see this characteristic curve, that how do we get this characteristic curve. So what we derived here is, we saw that as you increase the field current, so the idea was that as you increase the field current, you change the EA, you increase the EA, but EA cannot increase randomly. It needs to supposed to be aligned along this line. You cannot go anywhere else. It means an EA plus some vector is supposed to reach v5, which imposes the condition that IA's angle should change. Okay, and IA's magnitude should change. It means the IA, it will affect the IA, and it will affect the power factor as well. So so if I have all these vectors, so let me explain the diagram here. So this is the same diagram, only what I'm doing is that what we are doing here is that we are varying the field current, and because of the field current we are increasing the EA. And so EA vector is shown in the blue line, which is the this point, and you have the XS component, which is the green line, that is also, and the black is the V phase, which is addition of the blue and green, which is blue is the EA and JXI. Okay, and now we want to see is that we want to run this animation for the different field currents, and now want to see, okay, how does the field current tracks, how if we vary the field current, how does the armature current changes. So let's run this animation. What you saw here is that as you increase the field current, your point started from here, which was the lagging power factor load current, and then it went down. The current, basically the magnitude of current, decreased till this point. So this point is happens when your power factor is equal to unity, which is the unity power factor, when the IA is perfectly aligned with the V phase. And then if you further increase the field current, you will increase the magnitude of the field current, but now you have, so towards the left of this line you have a lagging power factor, and to the right of this line you have a leading power factor, and the minimum occurs at the unity load. And these type of a curve is called the V curve for the synchronous motor. And it's a very useful curve when we are operating as the synchronous motor to operate as a power factor correction device. So now you can see on your left that we have a different V curves for the synchronous motor as we increase the field current for the different power levels. So remember, we had the assumption that our power was constant. So what we are doing here is that we are increasing the power level, but for the whole experiment, whatever the power is, that stays same. So each curve represents different power level. Okay, so it means that all curves will have a this line, which is the unity power factor line, which is the dashed line, and you'll have a lagging power factor and you have a leading power factor. So just to share one more observation here, that when you are operating as a lagging power factor, that is called the under excited synchronous motor. In under excited synchronous motor, the EA cos theta is less than the V phase. And if you are operating as a leading power factor, so that is called the over excited synchronous motor, and that in that case the EA cos theta term, which is this component, that is greater than V phase. So I think we will stop here, and we'll discuss one example in our question and answer session if we have the time, or if we have more questions, then we'll just take the questions. And so I'll see you next time in the Q&A session. Thank you very much. Allah Hafiz.